Hi, everyone. This is the Hungry Math Professor here, and thank you for coming to my channel. Today, I want to talk about The Structure of Scientific Revolutions by Thomas Kuhn. I just finished reading this with my philosophy discussion group. We had a good discussion, and this book was published in 1962 originally, though it's in its fourth edition, and I have the 50th anniversary edition, which is the fourth edition. So it's been revised several times, partly because of how popular the book is and also how much sort of pushback it got. And so uh, it's required some attention in that sense. Um, this in particular, there is an introduction by Ian Hacking, which is nice to read. And there's also a postscript by Kuhn, which was already added to the second edition in 1969, where he addresses some of the popular criticism and also kind of sticks to his guns, but tries to um, put some of his ideas in a different light. What's interesting here is that Kuhn got his PhD in physics in 1949 from Harvard University, but starts to get interested in the history of science, in particular the history of physics, um, in as a postdoc. And then the structure of scientific revolutions, as Kuhn uh, makes very clear in the first chapter, is in his mind a work of the history of science. But when you read this, you're going to also, it's going to be hard not to feel like there's at least some implicit philosophy going on. Maybe not explicitly, he's not diving headfirst into the philosophy of science, but by the nature of what he's writing, there's implicitly lots of philosophy to read between the lines here. But Kuhn presents himself as a historian of science, someone who knows physics in particular very well because he studied physics in grad school. But as if you read the text, you'll notice that almost all of his examples come from physics and chemistry. And he only once uses evolution in biology, um, as an example, but almost all of his examples come from physics and chemistry. So I think when you read this, you have to think of the word science in Kuhn's mind as being maybe just physics, but certainly given his examples, physics and chemistry, and sometimes biology, depending on how you think about it. So I think roughly you can say physics, chemistry, and biology. But if you want to criticize Kuhn, you might want to say that he's really just talking about physics, since that's the thing he knows the best. Um, let's stay agnostic about that particular point, but I think it is worth bringing up, like, how broadly does Kuhn's ideas apply to science, and what is science in Kuhn's point of view. Again, from the very beginning, Kuhn's saying, like, if you study the history of science carefully, the first thing he wants to point out to you is that this idea that science progresses linearly and makes this kind of progress towards truth just doesn't seem to be borne out by historical evidence. That's his, I think, main thesis from the very beginning. And he wants to try to look at the history of science and provide some kind of conceptualization of what is going on in the community. Again, it's not going to be this like linear progress towards some kind of scientific truth for Kuhn. Um, and so the question is then, what is going on in the scientific community? Again, even with the way I just presented it, I'm presenting it maybe with a more philosophy baked into what I just said. But Kuhn is, I think, tries to be very careful about, though he fails at times, but he tries to be very careful at just kind of describing the history of science instead of taking too much stances on the philosophy of what this all means for science. Okay, let me try to present a little bit of what he brings in mind. So the first thing that Kuhn brings up is this concept of normal science and puzzle solve. Okay, so normal science for Kuhn is what scientific communities do most of the time. Um, and so what does that mean? Like, I must also admit my own bias. I'm a math professor, as you might know from my channel. My research area is most closely associated with general relativity, and I've done some work in general relativity. I'm not a physicist. I'm not trained as a physicist, but I understand general relativity fairly well from a mathematician's point of view. And so most of my examples, or most of how I think about things, come from general relativity. Um, so, one way to think about it is you have Einstein's equations, and then what is normal science? Well, it's trying to better understand Einstein's equations. One example I can think of is Emmy Noether, who early on in general relativity was brought in to work with Einstein and to try to understand conservation of energy. How does conservation energy work in Einstein's equations, in Einstein's theory? And Emmy Noether wound up developing this beautiful um, theory that conservation of energy is related to symmetry in physics, right? Which has sort of been a beautiful idea in physics ever since. And this is called Noether's theorem about how symmetry is related to conserved quantities in physics. Um, and that idea is somehow clarifying Einstein's theory of general relativity, right? And then also Einstein's equations are extremely hard to solve a lot of times. So, another thing of normal science can just be solving these things in lots of different situations, right? You're not you're not challenging the you're not challenging Einstein's equations by doing that. You're not saying, well, maybe we should consider other equations, right? Normal science from Kuhn's perspective, is accepting Einstein's equations and then tinkering them and improving them and applying them to lots of different situations. And this is an example of what he sees as normal science, right? You're not going to challenge the foundations in any kind of revolutionary way. Instead, you accept the foundation of general relativity as generally true, and you're constantly trying to tweak and improve by maybe getting better precision on physical constants that occur in Einstein's equations, or solving the equations more carefully, or clarifying, conservation of energy, these sort of theoretical issues that occur. And then lots of experimental research where you're trying to confirm more and more and show that Einstein's theory gives good predictions, so on and so forth. Right? This is an example of what he thinks of as normal science. And I'm sorry if general relativity is not the most accessible example, but it's the example I have. And I would encourage you to read Thomas Kuhn for many other examples. He gives lots of examples in chemistry and also early astronomy and things like that. But he says that, like, what needs to happen at some point for every scientific field is the acceptance of some kind of established foundation for the field. I'm avoiding a certain word that I'll use in a second, but he says that they need to sort of, at some point, they establish a foundation for the field and organize themselves around that foundation. And he says in a pre-paradigm period, okay, I got to start using it. In the pre-paradigm period of a science, there's like somehow too many competing foundations around, too many competing paradigms. And because of that, they struggle to talk to each other, and they struggle to make sense of what the experiments are saying. But he says in Kuhn's description, at some point, the community of a particular scientific field will coalesce around a foundation. He used the word paradigm. And when they coalesce around a paradigm, then they come into a period of normal science where the field mostly agrees about the paradigm, and where they disagree are in the details, the sort of what he calls puzzle solving of everyday normal science. And so there might be some heated disagreements about how puzzles should be solved or what they mean, but they don't disagree about, like, the paradigm or the foundation that sets in motion and organizes the particular scientific community around a particular field. Okay, I've already sort of let the cat out of the bag. One of the big words that Kuhn uses and really makes popular is this word paradigm. But also, he gets criticized quite a bit for how widely he uses this word. And so people accuse him of just being so confusing. Like paradigm feels like it can mean almost anything for you at so many different levels. Actually, while I was reading the book, I could notice this, but I didn't see it as a bad thing. Paradigm could be as small as like one equation, it feels like, that is fundamental to a certain area, or it could be like principles at the top level of science that we see as like important, um, or different beliefs that scientists have about how science should be done. That's a lot of different ways you can use the word paradigm. But in the postscript that he wrote in 1969, he tries to clarify this, right? Because there was this paper written, and I'm sorry that I forget who wrote it now, where they claim that Kuhn uses the word in 22 different ways. And that doesn't sound good. So he tries to clarify that, okay, 22, most of these differences he thinks he could clean up by in very simple ways, and they're not major problems. But he acknowledges that there's probably um, two ways that he should have organized paradigms, and he says that there's like this very global sense of paradigm and there's very local sense of paradigm. And he goes through and gives sort of four different senses of what he calls the disciplinary matrix that organizes the scientific community. And he's saying that the word paradigm is very much about um, trying to understand the organization of a scientific community. I do want to read one quote where he discusses how he conceptualizes a scientific community. So for Kuhn, he says, a scientific community consists on this view of the practitioners of a scientific specialty. To an extent unparalleled in most other fields, they have undergone similar educations and professional initiations. In the process, they have absorbed the same technical literature and drawn many of the same lessons from it. Usually, the boundaries of the standard literature mark the limits of a scientific subject matter, and each community ordinarily has a subject matter of its own. There are schools in the scientist communities, that is, which approach the same subject from incompatible viewpoints, but they are far rarer than in other fields. They're always in competition, and their competition is usually quickly ended. As a result, the members of a scientific community see themselves and are seen by others as the men uniquely responsible for the pursuit of a set of shared goals, including the training of their successors. Within such groups, communication is relatively full and professional judgment relatively unanimous. Because the attention of different scientific communities is, on the other hand, focused on different matters, professional communication across group lines is sometimes arduous, often results in misunderstanding, and may, if pursued, evoke significant and previously unsuspected disagreement. Okay, so he tries to point to this idea that scientific communities are rather unanimous, and there tends to be agreement among a local community, though when sort of one subspecialty tries to speak to some other subspecialty, there might be a lot more disagreement than they expect. In general, each subspecialty tends to coalesce around each other, around a sort of shared set of ideas of what science is and what their field is about. He goes on to explain what he calls now the disciplinary matrix as a way of trying to further differentiate what he means by paradigm. He lists four different um, things that are in the disciplinary matrix that sort of organize the scientific community. So one of these things is symbolic generalizations. And one example of this comes from Newton's Newtonian mechanics, where we have this F equals ma. From a purely symbolic point of view, that's just three letters in an equation. Of course, these letters mean some things, right? F is for force, m is for mass, a is for acceleration. And he's saying that this symbolic generalization of F equals ma organizes Newtonian mechanics in a lot of ways around this symbolic generalization. But he also points to later that, you can't just apply F equals ma in practice. You have to learn what that means in lots of different applications that you want to apply Newtonian mechanics to. Meaning, oftentimes when you're given a physical situation that you want to study, you have to figure out how to quantify the force. That's the trickiest part. And when you take physics, and if you're doing Newtonian mechanics, you will have to learn in various different situations how to express the force in a way that's useful. And oftentimes this means converting to some kind of differential equation. And so you need the force to be expressed in a way that is amenable to the tools of differential equations, right? The mathematical toolbox. And he points out that like the equation itself doesn't teach you how to do that. And the way that physicists are taught to figure out how to find this force, how to express it in a useful way, is by doing lots of problems. And these problems help to hone in your intuition about how to find the force. And of course, these problems are designed by experts who are already in the field and who have already gone through similar problems and are checked by those same experts, right? Your professors that you might have as you're going through this training. So there is this sort of self-fulfilling um, training going on, which happens in all fields, but he's saying that like in order to really understand what F equals ma means, you have to do lots of problems and develop a working intuition for how to work with how to use these things, right? And those that training is given to you by textbooks and by the professors who have already been trained in this field. And so, he's going to argue that serves to further, coalesce the community around each other because, you teach your students to follow in your footsteps is in a certain sense. Okay, so that's one of um, the things that Kuhn identifies in the disciplinary matrix, which is symbolic generalizations. Then he talks about metaphysical paradigms. Something that's interesting that came up for me in the first time in this book, which I feel almost a little embarrassed to admit because I think it's something I should have realized earlier. I'm glad to have been exposed to it here, is this idea that the scientific theory itself, which is accepted, or the paradigm, which is in place, or the foundation, however you want to think about it, also determines what is considered physical versus what's considered metaphysical. What do I mean by this? Well, in Newtonian mechanics, there's constantly all these force vectors all over the place. Yeah, and because the theory of Newtonian mechanics talks about force vectors so much, it feels like that is a part of physics, or even maybe a part of the world, or something you're entitled to talk about, right? But you might want to call other things metaphysics, like usually the science community, when they talk about metaphysics, it's in a pejorative sense, like the things that we're not supposed to talk about, right? But because force fields are a part of Newtonian mechanics, it gives the impression that you're allowed to talk about force fields, and maybe you're even allowed to project them onto the world in some sense. But maybe other things you're not allowed to talk about because those are just metaphysics, and just leave that for the philosophers, right? So my point here is just that what is considered metaphysics versus what is considered physics is often relative to the particular paradigm or the particular set of equations or theory that you are investigating. And if that theory changes later, it will change what is considered physical versus what is considered metaphysical, or at least it has the potential to do that. And so it just points to this idea that this distinction between physical and metaphysical is not a very solid distinction, and it's often relative to the particular physics or paradigm that you have in place, what is considered metaphysical versus physical. Okay, the third thing he identifies as values, like each of these scientific communities, but also the science community as a whole has lots of different values which it holds as a community. And for one, it could be like predictions. What is considered a reasonable measure of accuracy in a particular field? What is considered sort of too imprecise to be considered a good prediction? What is desired from theories. Oftentimes in general relativity, there's this idea that physical theory should be beautiful in some sense. There's somehow an aesthetic criterion which is seen as a value of science. And then he talks about how some communities might think that science should be socially useful, and other communities might think that science does need not be socially useful. They could disagree about that value. And then there's like a lot of the principles of science that you'll learn about in like the general scientific method, things like simplicity, over complicated theories, precision is desirable and generality is desirable. And there's these principles of the scientific method. So there's all kinds of different values that a scientific community can hold that can make it well defined as a community. And then the fourth thing that he um, points to is exemplars. And here I think he does a lot of work with exemplars to try to explain his feel to explain his point of view on the scientific community. So again, I've already sort of talked about this as F equals ma is an important bedrock to Newton's theory of mechanics. But in order to really understand Newton's theory in practice, you have to study many exemplars or examples, which teach you how to translate F equals ma into a useful form in all different kinds of situations, depending on what you're studying, right? Where you're studying a pendulum or spring mass system or so on and so forth, all kinds of different situations where you need to do this. The same thing is true in Lagrangian mechanics, where you are taught this thing called the Lagrangian, but then in any various different situations, you need to learn how to actually find what the Lagrangian is. And the way you learn how to find these things is by doing many examples. So Kuhn really talks about how the textbook is in such an important part of the scientific community in training its new members in the sort of established orthodoxy of the paradigm of the time. Okay, so these principles that he calls the disciplinary matrix also make up what he calls a paradigm. And, you can try to understand more deeply what he means by a paradigm. But you should also understand that people have criticized him for using this word in too many ways. But I presented sort of how he tries to address this in the postscript that he wrote in 1969. Okay, so again, this paradigm is what he considers to be accepted in the mode of normal science, which is sort of the mode of science that he thinks occurs most often. Okay. But he talks about how in the process of puzzle solving, which is what happens in normal science, you keep getting more and more and more precise predictions, more and more accurate, more and more understanding of the current paradigm. And eventually this constant puzzle solving that goes on leads to a level of detail that eventually causes anomalies to crop up. And these things, these experiments or these issues with the equations or whatnot that just aren't quite fitting the theory in the way that you'd like and fitting the paradigm. And if enough of these anomalies occur, or if they seem important enough to the community, they can cause a crisis where people start to wonder whether this paradigm is actually up to the task of explaining these anomalies, right? And so for Kuhn, this is where a transition happens between normal science and then this crisis period. And in this crisis period, now people are willing to consider alternative paradigms. And whereas in the period of normal science, this would be seen as, unscientific or, blasphemous to try to do that. In these crisis moments, it feels like the community is willing to, or feels like it's necessary for the community to look for possible other paradigms to explain these problems. So one example of this, of course, is going from Newtonian mechanics to general relativity in the early 20th century. And what he talks about is during these crisis moments, you'll have these competing paradigms. And then often a revolution occurs and you transition from one paradigm to the next. So again, from Newtonian mechanics to Einstein's theory of general relativity as the paradigm for gravity. And what he tries to point out in these revolution periods is that oftentimes when we look back in history, the scientific community will present a version of this crisis and revolution uh, transition where it is presented as progress. And I can attest to the fact that the way I was taught about, the transition from Newtonian mechanics to general relativity was presented as progress, and I've always seen it that way. And so it's interesting. I enjoyed this as just like a challenge to me to ask the question, is that true? Because I do see philosophy as about challenging these sort of deep-seated assumptions that we make. So, at the very least, we should accept this challenge, and we can wonder whether Kuhn is right about this or not. Um, so what he says is that when a revolution happens and then a new paradigm is accepted, you rewrite the textbooks. And when you rewrite the textbooks, you do always present the most recent last paradigm. So you would present Newtonian mechanics, but you do it in such a way so that it fits in the story of progress. So you emphasize the parts of Newtonian mechanics which then are, that grow into sort of more precise things in Einstein's theory of gravity. So, like one example of this that's always presented, there's many examples that go from Newtonian mechanics to Einstein's theory, but one example comes from special relativity, where in Newtonian mechanics, speeds are always additive, right? If I'm on a rocket ship and then I throw a ball at a certain speed, the speed of that ball is going to be the sum of the speeds that I threw it at and the speed of the rocket, this kind of thing. But in special relativity, that can't be the case because nothing can travel faster than the speed of light. And so if speeds were additive, then I would be able to throw something faster than the speed of light by just sort of, adding two speeds in such a way, right? So this is a problem. But in special relativity, this is fixed by giving a different way. The speeds are not additive. They follow this equation that I don't want to say out loud because it's not going to help anybody who doesn't already know it. But basically, the way the story goes is you show how, okay, there's this other way that speeds combine, and then, but in, small speeds, the kind of speeds we observe in everyday life, which are, even like speeds of rockets are relatively low compared to like the speed of light or things that can happen um, in the universe. You show that, oh, well, it's a reasonable approximation to the speed that special relativity tells us is correct, right? So that this additive speeds is a reasonable approximation to what special relativity tells us is true in low speeds. And of course, this is a useful thing to teach students, so I don't think we want to criticize that too much. But Kuhn is arguing uh, that this is what science does all the time in rewriting history. And also, he tries to point out, he uses this word incommensurability, which is to say that, yes, it's useful to see that, additive speeds is not quite correct, but a useful approximation of small speeds to special relativity. But in some fundamental sense, Newtonian's theory of gravity and Einstein's theory of gravity are completely incommensurable, right? They as complete theories, they are logically incompatible with each other. So it's nice to see to see Einstein's theory as like a progress in from Newtonian's theory of gravity, but he's arguing that they're completely incommensurable. So what kind of progress are we talking about, right? And he also claims that the problems that one theory addresses versus what the other theory addresses are very different. And in fact, this is a good example because Newtonian mechanics is still used in so many areas of engineering and even in physics because it's still somehow often the best way to try to study physical situations. And Einstein's theory of gravity is too complicated for most things that we want to do on Earth, right? In order to really need Einstein's theory of gravity, you usually have to be studying something in the universe, right? You want to be studying maybe the motion of planets. Even then, it depends on how complicated a system you want to get to. You want to be studying things about black holes. I mean, one typical example of the use of Einstein's theory of gravity that is practical is for satellites. The timing of satellites requires the kind of precision that Einstein's theory of gravity provides um, versus what Newtonian's theory of gravity. This has to do with time dilation, which comes up in Einstein's theory of gravity that's not present in Newtonian theory. But satellites is just one application, right? Uh, so he points to the fact that these things are completely incommensurable theories, and he says that that's always the case between paradigms. I'm just using Newtonian mechanics and Einstein's theory of gravity as a prototype because it's what I like to think about. But he's claiming that this is true of all revolutions in science. It's between one paradigm to the next, that there's always this incommensurable nature, and it's never the case that the number of he claims that it's never the case that the number of experiments which are explained by the previous paradigm is somehow more by the new paradigm. He says really the number of experiments that are explained are just different. And perhaps they are just more useful to the current society. And that gives the illusion of progress. But in the case of like getting closer to the truth, I think he's claiming that, it's not clear that you've really gotten close to the truth, but rather you just explained things that feel like more important to the current paradigm. But I mean, it's interesting because if you think about Newtonian mechanics and Einstein's theory of gravity, if you think about how it actually comes in practice, again, Newtonian theory of gravity gets used in so many different places. So in some sense, it has not been replaced. It's simply been delineated into different regions, right? Like in certain areas, we use Newton's theory of gravity, and it's extremely useful in engineering and things like that. And in other areas, we use Einstein's theory of gravity. And if these theories are completely incommensurable, then, in what sense is one more accurate than the other? One is more true than the other, is what Kuhn is trying to bring up. Um, he talks about how when you switch from one paradigm to the other, um, there's this, the community is in crisis. They have to decide whether they should stick with the old paradigm or go to the new one. Um, he talks about how there's a breakdown in rationality that occurs there because the assumptions that one paradigm makes about how the world works and how we should do science in some particular sense is very different than the assumptions that the other paradigm makes. And he also makes a very strong claim that the way they see the world is different. If you think Newtonian gravity sees all these force vectors all over the place, and Einstein's theory of gravity sees somehow this Riemannian or Lorentzian geometry as being responsible for gravity. And how do one talk to the other, right? In this crisis period when they haven't accepted one versus the other. And he talks about how the way that you choose between a paradigm is not so much like a logical argument because your assumptions are so different. Instead, it's more like this social decision that has to be made. And oftentimes he talks about how it's the younger members of a group who tend to be more open to revolutions, and the older members of the paradigm or the community who have been in that paradigm for so long who are not open to this. It's funny because Einstein is a good example of this because early in his career, when he was young, he was very willing to be revolutionary in the development of special and general relativity, and oftentimes cited later in his life as being not open to the revolutionary nature of quantum mechanics, right? This famous quote of Einstein that God does not play dice. And oftentimes that's presented as a mistake, which Einstein made by, not being open to quantum mechanics. But I think the way Kuhn seems to present it is it's not a mistake, that there's nothing illogical about one paradigm holding on to its point of view versus another, because again, these paradigms are, in Kuhn's view, completely incommensurable, and neither is illogical. So from Kuhn's perspective, the way I see it, Einstein just lost a community discussion in some sense, right? Like he lost an argument between his community, and quantum mechanics in some sense wind up winning that, with the probabilities that come with that, wind up winning in the sense of coalescing around that particular idea. And rejecting some of Einstein's critiques. So in that sense, Kuhn sees it as, you're not, it's not that Einstein was wrong, it's just that he did not, he lost control, or he lost a argument between his community. I think that's an interesting way of thinking about it. Um, you know, he talks about how, why then do we not see these revolutions in, like, why do the scientific communities don't really see these revolutions in this way, like in this incommensurable way? And again, I've already kind of mentioned this, but he talks about sort of in the last chapter how it's the community itself which sort of rewrites history to fit their narrative of progress. And it's the textbooks primarily, which he says are the way in which the community does this. That might sound very negative, but I think Kuhn doesn't even see it as very negative. He thinks that normal science is an extremely important part of what makes the scientific community so valuable. And so, in some sense, I think he thinks that they should almost rewrite history to create this coalescing effect for the community. And that creates this period of normal science, which in turn gives us so much ability to solve problems very carefully, and we get so much precision from that, and we get technology, and so he seems to be very positive about that, even though it sounds negative to say that these paradigms are these scientific communities are sort of rewriting history to feel like progress in order to create this period of normal science. Um, but he is trying to point this out because he's a historian of science, and he's trying to, again, I'll end this discussion with how I kind of started it. He's saying that, as a historian of science, when he looks at science, the history of science, he just doesn't see this progress that people keep talking about. And so what is the historian of science to do, right? Again, so just to recap, and then I'll end here. Kuhn sees the history of science, and presumably how he thinks science is going to go forward, as a constant back and forth between a period of normal science where a particular community coalesces around a paradigm, a shared set of exemplars, and gets into a period of normal science, which involves a lot of puzzle solving. These puzzles can involve various different things, theoretically, experimentally, and in the development of apparatus and things like that. Until the precision of things gets so careful that inevitably anomalies come up that the paradigm is not able to handle, then you get into a period of crisis where you need to consider various different paradigms. These paradigms are incommensurable with each other and cause communities to see the world very differently from each other, and and the way that you choose between paradigms is more of a social, more of like a political process between a community. And then at some point, there's a revolution that happens, and a new paradigm comes into play. And that new paradigm rewrites the recent history in order to make it look like progress, in order to cause the community to coalesce around a period of normal science again. And it's constantly this sort of tension between the period of normal science, crisis, revolution, and a new period of normal science with a new paradigm. So that's Kuhn's ideas. It was very provocative, and there's been lots of pushback and discussion about that. There's also lots of discussion about whether Kuhn's model applies to how science has been the last 25, 50 years. And there's a lot of discussion about whether Kuhn's model applies more broadly to what we consider to be science now. How does this apply to psychology and sociology, anthropology, and all kinds of different areas of biology and things like this? And so I won't get into all this, but please take a look, read this book. Let me know what you think, comment, like, subscribe, and I hope to see you at another video.